Okay, so we're going to get started. If other people pop on, great. Throughout the night, if you have questions, just send them to me, shoot them through, and we're going to hit sort of the major, more difficult topics here. Everything we're talking about today is an AP question. Please send questions if you have them, and we're going to start just with a basic overview and then go from there. Again, if you need the remind code, it's right here. Feel free to send me questions if you're watching this live. If not, you can still send me questions or send Miss Belden questions if you're in her class. So let's talk about fundamental theorem here. This is all from your notes. The only thing I added in new on this that's not directly on your notes is the mean value formula. So first off, this is the version of fundamental theorem that we started with first, which was that if I'm taking the derivative of, if I'm integrating a function, f prime, from a to b, what I'm really doing is taking the antiderivative, and then I'm plugging, I would have to be able to spell antiderivative. I'm plugging in my upper bound and subtracting out my lower bound. And this is the whole idea that the integral is actually equal to the net change of the antiderivative, or of the original function. Okay, this is just a transformation of that. So what I did is I added f of a to the other side. F of b is f of a plus the integral from a to b of that. And this is the big thing we need to know with that. To find a current value, you're going to do your initial value plus your net change. So a of t is a of 0, your initial, plus your net change there. Here's where this is often used. Again, we talked about this in class. To get a current position if you know the rate of change. To get a current velocity if you know the rate of change. To get a current amount of something if you know the rate at which it's changing, whether that's temperature, whether it's water, whether it's people entering an amusement park, whatever that may be. Derivatives of integrals, remember that those are inverse functions. That's why the fundamental theorem is so powerful. It relates the derivative to the integral, and this right here is a major part of that. So what it says is, if I take the derivative of an integral, well, I know that those are inverses, they undo each other. So if I'm starting with a function f, that's actually going to be what is in my answer. And right here, this should actually be, let me fix this really quick, just f, not f prime. So that should just be f. We fixed that in your notes. So what I'm going to do is I'm going to plug my upper bound into f, plug that into here, and that is f of g, and then multiply by the derivative of that, which is g prime, and plug my lower bound in and multiply by the derivative of that, which is h prime. Okay, that's the most general case. Here, again, this bottom bound was a. When you multiply by the derivative of a, it's 0, so that goes away. And then the last thing that we talked about was the average value of a function. So the average value of a function is 1 over b minus a times the integral from a to b of f of x. So for instance, if you're doing the integral, or if you're trying to find the average value of x squared on the interval from 1 to 5, you would have 1 over 5 minus 1, or 1 over 4, times the integral from 1 to 5 of x squared. And that would give you your average value of that function. Not the average rate of change, just the average value. Okay, so those are kind of the big ideas that we're working through. This, we're going to start kind of small. We'll go into some word problems. If you have specific ones that you have questions about, send them to me. But we're going to start with these two. So on these two, I'm looking at just the basics here. Finding the derivatives of integrals and how that might be useful. So I'm actually going to start on letter B on this one. And again, this is in that last notes packet. All of these questions are in there. So what I see here is that, I'm going to start with B. Capital F is an integral defined function going from x to 3 of this function of t. And I want to find f prime of x. So f prime of x is really saying take the derivative with respect to x of this. Right, taking the derivative of both sides. And if I think about that, well, I'm going to need to plug in my bounds, right? So plugging in my upper bound, I would be plugging in 3, but then I'd be multiplying by the derivative of 3, which is 0, so this just becomes 0, minus. Plugging in my lower bound, that would be the square root of 1 plus x to the 16th times the derivative of x, which is just 1. So this becomes the opposite, or negative 1 plus x to the 16th. that is the derivative of that integral defined function. So looking at letter A, how might we apply this, right? So on letter A, I'm given this function, and I have from c to x of f of x. So that's my integral on the right side. Part 1 says find f of x. And so what I think about immediately is, well, that's got to be something to do with this side, right? So I know that what I want is this x to go in as my input. And so I think that probably means I'm going to need to take a derivative. So what I'm going to think about here is doing the derivative with respect to x of both sides of my equation. Because as long as I do it to one side and I do it to the other, then that shouldn't be an issue. So integral from c to x of f of t dt. And remember, c is just a constant, so ultimately your derivative of that will be 0. So derivative of the left side, this would be 15x squared plus nothing, derivative of 40 is 0. And that equals the derivative of the right side, which is just f of x. So this is my derivative of the left side. So that is f of x. Okay, so we're going to come back to part 2 here. This is a little bit more challenging, but I want to make sure that we get through a couple of these other ones, and then we'll come back to that. So looking at this one, this is from the 2003 exam. This is a multiple choice. These come up a ton on multiple choice because it's very skill-oriented, right? So what is my derivative of this? Well, looking at this, I am thinking about plugging in my upper bound first. Derivative of an integral, right? They undo each other. So this is going to be sine of t cubed, so x squared cubed, times the derivative of that, which is 2x, minus, and now on the bottom, it's not going to matter because it's 0, and the derivative of that is 0. So what I really get here is that this is 2x times sine of power to a power, multiply your exponents, x to the 6th, so 2x sine x to the 6th, so that should be E. One that I'm going to talk about is this. G is defined as the integral from -2 to x of f of t, where f is the function whose graph is shown. The first thing I do when I see this is I look at this and I say, okay, I don't even know if they're going to ask me about it, but G prime here would be f of x, and just doing the same thing, plugging your upper bound into this, the derivative of that is 1, plugging your lower bound in, the derivative of that is 0, so it's just f of x. And so what I know here is that this graph is actually G prime. Okay, so when I am asked about mins, max, increasing, decreasing, concave up, concave down, I know that I'm looking at a graph of the derivative, and then it's a curve sketching problem. Then I could have given you this problem in November, and you would have been fine. So, part A says evaluate all of these integrals. And evaluate that means find the area under the curves, because you're doing G from this value to some other value. So I'm going to start by actually calculating some of my areas. So this is a triangle. It is 1 by 2, so it'd be 1/2 1 times 2, so I just need an eraser. This would have an area of 1 unit. Now, these are a little bit harder. You need to actually calculate where that crosses, which is at 1/2, and I can see that because it goes from here to here in one box. So this is going to be 1/2, 2 times 1/2. So this actually has an area of 1/2. This has an area of -1/2. Now this area right here, these two boxes, I see that that's 2. And I'm breaking this up into small intervals because it will make it easier to actually do my integrals in a second. And that's below the x-axis, so I'm thinking about that as -2. This one right here is a little tougher to figure out, again, because it's not crossing it like a nice even point. So let's kind of figure out where that crosses. So this right here goes 2 boxes over, and it goes up 1, 2, 3, 4, 5, right? It goes up 2 boxes over, it goes over 2 boxes over and goes up 5. So its slope here is 5/2. So every one box, this will move over sorry, hang on one second. I just got to remind. So this slope is 5 over 2, right? So then the question is, well, how far is it moving in 2 boxes, right? So, or in 1 box. That's not what the question is. Okay, hold on. We got to find this intersection point. So this is our slope, right? So here this is at -2, right? So I'm going up 5 over 2 for every 2. So this is up 2.5 over 1. So I could figure out here, this would be up 2.5. So this would be, yeah, that's where that is. So what I really need to figure out is this intersection point right here, which for some reason on a Sunday morning, my brain is having a brain fart with. So I need to figure out when that will equal 0. So I'm going to think about this function. So what would my y-intercept be? I would be going down, in one more box, I would be going down 2.5 and left 1. So if this is at -2, your y-intercept would be at -3.5 or 4.5. So the equation of this line is y equals 5 over 2 x minus 4.5. So where would that equal 0? I'm going to set it equal to 0. So this would give me 0 equals 5 over 2 x minus 4.5. So 4.5 is 5 over 2x multiplied by 2/5 or by the reciprocal of that. So that would be, I'm just going to make this into a fraction, 9 over 2 times 2 over 5. This would be 9 over 5. So my x coordinate there is 9/5. 9/5. There's an easier way to figure that out, but that's where my brain was today. So think about your area here. This area is 1/2 your base, which is 4/5 times your height, which is 2. And so this area is actually just -4/5. That's not pretty, but they can do that on the UP exam. And then thinking about your area here, well, this height would be 1 5/5, or 1 1/5, right? So 5 6/5 times your height, which is 3, and multiply that by 1/2. So that is 9 over 5 as your area. Okay. Sorry, that was slow. So A here, so G of -1 is the integral from -2 to -1 of f of t, right? -2 to -1. So -2 to -1, that area is 1. G of 0 would also just be 1 because here you're doing 1 plus 1/2 minus 1/2, right? And that's how you're going to do all of these. So you'd continue with, G of 1. So we're saying we're going from -1 plus 1/2 minus 1/2, that's just 1. Add in another -2, so that's -1, right? And you could keep going from there. So that would be how I would calculate part A. For part B, now I'm looking at, well, where is this increasing? So let me shrink this down. Where is G increasing? So you can go through this logically. You just have to think through what's going on there. But where is this increasing? G is increasing wherever G prime is greater than 0, right? So I know that this is my graph of G prime. So where is that greater than 0? So it's greater than 0 from -2 to -1/2, and then again from 9/5 to 3. So that's my interval where this is increasing. Why? Because on those intervals, G prime of x, which is f of x, is greater than 0. So G prime of x, which equals f of x, is greater than 0. Now, where does g have a maximum value? Okay, so here it will have a maximum. G has a max when, think about it, you want g prime to go from increasing, or g prime to go from positive to negative. Change from positive to negative. And this is my shorthand. This is just me making notes for myself. So from positive to negative, I see that happens at x equals negative 1/2. And it asks me why, and I would say because here, g prime of x, which is f of x, changes from positive to negative. So it becomes a curve sketching question at that point. Okay, last one. So on this one, we've got our integral from -2 to x of f of t, where f is the function shown. Stop before you go any further. We're going to say that means that g prime of x equals f of x. Plug in your upper bound. So this is g prime. Where is g increasing and decreasing? Explain your answer. So I'm going to look at g will be increasing when g prime is positive. So anywhere that f is over the x-axis. So it's increasing anywhere here. And it's decreasing, let's make the color even different, anywhere here. So here I would say g is increasing on, and then talk about your intervals, -1 to 0 and 2 to 3, because g prime of x, which equals f of x, is greater than 0 on those intervals. And then for decreasing, I'm going to say the same thing, but I'm going to change my intervals. And so g prime would be decreasing. I'm going to erase this little baby. G prime is decreasing on the intervals from -2 to -1 and from 0 to 2, because g prime of x, which equals f of x, is less than 0. So again, it just becomes a curve sketching problem once you know. Continuous, it's defined on this interval. The graph consists of 2 quarter circles. Generally assume that that means we're going to be finding some area, right? And 1 line segment as shown. G is an integral defined function. So g is 2x plus the integral from 0 to x of f of t. And the first thing when I do when I see any integral defined function is I'm going to take the derivative of that. So what I know here is that g prime would equal, well, the derivative of 2x is just 2, plus the derivative of the integral here is f of x. So here's what makes this a little trickier. That 2 out front is going to cause a little bit of a wrench in what we need to find out, but not that bad. So this graph is f. Okay, this graph is f. And g prime is 2 plus f. So first it wants me to find g of 3. It wants me to find g prime of x and then evaluate g prime of -3. So I've actually already done part of that just from anticipating what would be in here. So let's start with part A. I want to find g of -3. So g of -3 would be 2 times -3 plus the integral from 0 to -3 of f of t dt. So this is g. So I'm just plugging -3 in wherever I see an x there. And so, okay, this is going to be -6. The integral from 0 to -3, I'm talking about the area under the curve here. That is a quarter of a circle. So I'm going to be doing pi r squared. So 3 squared is 9 over 4 because it's a quarter of it. And because I'm going from left to right, or from right to left, sorry, this is going to actually be a -9 pi over 4. 9 pi being the whole circle, that's a quarter of a circle. So that is my answer for g of -3. For g prime of x, we actually already figured that out above. It's 2 plus f of x. And g double prime of x, g prime of -3 would be 2 plus f of negative 3. And so, well, how do I figure that out? So f of negative 3, I'm going to look at my graph of f. At negative 3, this is 0. And so this is 2 plus 0, which is 2. So the three pieces of my answer here are this part, and that part. So that's part A. Again, send questions as you have them. I'm happy to answer them. All right, part B is a little trickier. So part B says, determine the x-coordinate of a point at which G has an absolute maximum here. And so this is going to take some logic because it doesn't just say a relative max, right? So to be an absolute maximum, we want to either be an endpoint or we want to be where the most accumulated area is. So looking at this right here, my endpoints are right there and right there. And let's think about what's happening here. Here, I see that my function is negative, f is negative, and I see that my function is negative here. So in both of these cases, the function f is negative. G is going to be decreasing going to both of those endpoints. So I know to both of my endpoints, G is decreasing. Those are not going to be the maximums. But I see in here, if I actually look at what's happening, it's negative, and then all of this area is positive, right? And so it's accumulating more and more and more there. If this was just G prime equals F, this would be my absolute maximum because that would have the most accumulated area. But what we need to look at is that 2 plus here, right? So here's what I know for part B. I know for part B that G prime of X is going to equal 0 when f of X equals negative 2. Because looking at this function up here, it's 2 plus f. So if f was negative 2, I would get 0 for G, which is where my max will be. So I'm going to look at my graph here. I'm going to say, okay, where does that equal negative 2? It's right here. That value is at 5 over 2, or at 2.5. And so I think that that's where my maximum will be. That's where my maximum will be. So x equals 5 over 2. Okay, but let's try to think about why. So the reason why would be because G prime of X would be greater than 0 anywhere on negative 4 to 5 over 2. Right? Because this is above the line y equals negative 2. So anywhere here, I'm going to have a positive accumulation. Okay? And I know that G prime of X will be negative on 5 over 2 to, what's my upper bound here? 3, right? 3 is where I stop. And so because of that, that's how I can justify that this will have an absolute max. Because I know that it's going to be negative anywhere to the left of that. It's going to be positive anywhere to the right of that. Again, that one's tricky. All right, and then the last part says find all values of X on the interval where G has a point of inflection. So let's think about this. G has a point of inflection. So points of inflection happen when your second derivative changes signs, okay? So what I'm looking for here is where G double prime of X changes signs. So let's first find G double prime. G double prime is going to be F prime, right? Or 2 plus F of X prime. So if this is G prime, G double prime is F prime. Right, the derivative of 2 is 0, and the derivative of that is f prime. So, here's what I'm going to look at. G double prime, where is that going to change signs? Anywhere the slope of f changes signs. So I'm going to look at my graph. Where does that happen? Well, anywhere to the left of 0, anywhere here, my slope is positive. anywhere to the right of 0, my slope is negative. So this is going to have a point of inflection at x equals 0, because that is where G double prime changes signs, or F changes from increasing to decreasing, or however you want to phrase that. Okay, that was a tough one. So do we have questions about that? Take a second, look at it, see if there's anything you want to send me, and let me see what question I think I want to do next here. Okay. Anything on that? Send away. Again, that's a super tricky one because of that 2x. But if you have questions about it, let me know. Okay, let's look at, this was the answer key to that. There's your solutions. That was 7 out of 9 points on an AP. All right, this next one is about traffic flow. We're not going to do all parts of this, but we're going to do at least A through C, talking about the traffic flow at a particular intersection. So find this in your notes if you need to. So traffic flow is defined as the rate at which cars pass through an intersection measured in cars per minute. So immediately when I see that, I think that this is a rate and it's in cars per minute. So this I already know is a rate, right? So the thing they gave me there is a derivative, okay? The traffic flow at a particular intersection is modeled by this this function. F is 82 plus 4 sine t over 2 between 0 and 30. And again, cars per minute and minutes. So I'm going to look at A, B, C here for sure. So part A, to the nearest whole number, how many cars pass through the intersection over the 30-minute period? So we know that we're given the rate. What I want is the net accumulation of cars, right? The total change. So for part A, all I'm really doing is saying, well, I want the integral of f of t with respect to t, because I want the area under that curve, from 0 to 30 minutes, because remember my units are in minutes. If this was hours, you'd do 0 to a half. And we can just put that into our calculator, and this would come out to be 2474 cars. Okay, and on the AP, that was 3 points. So you got 3 points for getting that correct. 3 out of 9, 30 your points. All right, part B, is the traffic flow increasing or decreasing at t equals 7? So if I'm talking about something increasing or decreasing, I'm talking about the rate automatically. I know that. So I'm going to look at my rate and I'm going to say, well, is that positive or is that negative? And from there, I'll know whether it's increasing or decreasing. So I'm going to find f prime of 7. And again, you can do this by hand or you can just put it in your calculator. It comes out to be negative 1.872, or you could say negative 1.873. You can round or truncate. And now I need to think about what that means. So I see here that the traffic flow, that rate, is negative, right? That rate is negative. So since f prime of t is less than 0, since f prime of t is less than 0, the traffic flow is decreasing. Okay, and then the last part I'm going to do is part C, which is what is the average value of the traffic flow over this interval? Indicate your units. So average value, remember we said, is 1 over b minus a times the integral from a to b of your function. Right, that's my formula. So I'm going to use that for traffic flow. So my traffic flow, it's 1 over 30, because that's my interval of time. Or I'm sorry, it said over the first, from 10 to 15. So it's 1 over 5. The integral from 10 to 15 of f of t dt, because I want the average traffic flow. And again, just plug that in your calculator, and this is 81.899. And what are the units of traffic flow? Because that's really what this is. The units of traffic flow are, look back at the problem, cars per minute. So this is the cars per minute. Okay, continue to send questions as you have them. All right, send questions as you have them. I'm trying to find another good question to look at. Okay. All right, the next one I'm going to look at, I'm scrolling a little bit, is about water tank. All right, so it says a water tank at Camp Newton. If you are looking at your packet, this is in there, look for a water tank at Camp Newton. Again, we're not going to do all of this, but we are going to do a couple parts of it that would be most relevant to you guys on your test. Okay, so is the amount of water, a water tank at Camp Newton holds 1,200 gallons of water at time t equals 0. Immediately when I see that, an amount at t equals 0, I think, hey, this is an initial amount. That's an initial amount, okay? During the time interval from 0 to 18, water is pumped into the tank at this rate. During the same, water is pumped out at that rate. So I have an in and an out here, right? An in and an out. So the first thing it says is the amount of water in the tank increasing at t equals 15, why or why not? So if I'm looking at the amount of water increasing or decreasing, what I want to know is my rate of change positive or negative, right? Is my rate of change positive or negative? So what I'm going to look at for part A is my rate coming in versus my rate going out. And there's more than one way to do this, but I'm going to look at the rate that is changing. So rate coming in is W of t. Rate going out is R of t, and I'm going to subtract those because I'm going to do in minus out. Okay? And I want to know at 15. So what I'm going to do is W of 15 minus R of 15. And again, this can just go in your calculator. Make sure that you are in radian mode. And I'm going to get negative 121.090 for my rate there. So if I see that rate is negative, what I know is that the amount of water in the tank is decreasing. So because W of t minus R of t is less than 0 at t equals 15, the amount of water is not increasing, or the amount of water is decreasing at that time, right, at t equals 15. So that would be what I would be looking at for part A. For part B, to the nearest whole number, how many gallons of water are in the tank at t equals 18? So remember, this is your initial plus your net change, right? The amount at any time is the initial plus the net change. So the initial here, they told me was 1,200. So I was starting with 1,200 gallons in the tank. And my net change is going to be an integral. And we're going up to the 18th minute. So I'm going from 0 to 18. And now of what? Well, it's the amount coming in minus the amount going out. So the amount coming in here is W of t. And the amount going out is R of t dt. So this expression right here is how we can figure out our exact amount. So 1,200 is my initial. My net change is going to be the amount in minus the amount out. And so plug that in your calculator. Again, this comes to 1310 gallons. And it's set to the nearest whole number. All right, send questions. I'll wait another second. Okay, so let's look at part D on this one really quickly. So D says for T greater than 18, no water is pumped into the tank. But water continues to be removed at R of T at that same rate until the tank becomes empty. Let K be the time when the tank becomes empty. Write but do not solve an equation involving an integral expression that can be used to find the value of K. So here's the idea here is that I know that I'm only losing water now, right? We said in part B that at 18, this is how much was in the tank. So what I really know is how long is it going to take me to have that gone, right, to have that removed. So what I'm going to look at here is that this is going to be the integral from 18 to some value K, right, K is my time that this would stop, of the rate that it's being removed. So that tells me how much is removed. And if I want the tank to be empty, I would set that equal to 1310. So this would be my answer for part D. Okay, let's look at another one. So this next one, talking about cross sections of a tree. So at a certain height, a tree trunk has a circular cross section. The radius of that cross section grows at a rate modeled by this function. So this is the rate at which my cross section's radius is changing. Okay. Now, and already I see at t equals 0, r is 6. So this is my initial. The area of the cross-section is denoted by A of t. Again, we're not going to do all of this. We're kind of picking and choosing parts. So part A says, write an expression involving an integral. They are not shy. For the radius between 0 and 3, use your expression to find r of 3. So remember that my value at any given point is going to be the initial plus the net change. The initial plus the net change. The initial here they told me was 6. And the net change in radius is going to be the integral of my radius. So my expression here would be from 0 to time t of this function up here. So 1 over 16, 3 plus sine t squared. dt. That's an expression to find it at any time t. This would be r of t. And it says use that to find r of 3. So I'm doing 6 plus the integral from 0 to 3 of that same thing. And again, plug that in your calculator. And we get 6.610 or 611. So this would be my radius at that time. Okay, let's look at something else. Send questions as you have them, guys. It's been very quiet tonight. I am here for questions. You just need to ask. All right, let's look at another one. So this one's a pretty interesting one. We've got a graph and we've got some information here. So there are 700 people in line for a popular amusement park when the ride begins operation in the morning. Boom, immediately I see 700 people. That is an initial amount. Okay, that is an initial amount. Once it begins, the ride accepts passengers until the park closes 8 hours later. When there is a line, people move on to the ride at a rate of 800 people per hour. So this is the rate that people move on to the ride or out of the line, right? The graph shows the rate at which people arrive at the ride throughout the day. T is measured in hours, after the ride opens. So how many people arrive at the ride between 0 and 3? So let's think about this. People that arrive at the ride. This is the rate that people arrive. Okay, the graph shows the rate at which people arrive. This is the rate people get on. So part A says, how many people arrive at the ride between 0 and 3? So what I need to think about for that is the integral of the rate that they arrive. The function that they've given me a picture of is the rate at which people arrive, right? So to find the number of people that arrive between 0 and 3, I need to find the area under this curve. So I'm looking for this area in here. Right there, 0 to 3. So lots of ways you can do this. You can do rectangles. You can do whatever you want. It's sometimes easier, I think, to just break it up into trapezoids. So like this is a trapezoid, right? And you could average your 2 y values and multiply by your height. So it would be 2 times 1,000 plus 1,200 over 2. And then this one here would be 1,200 and 800 as your y values, and that's 1 wide. So 1 times 1,200 plus 800 over 2 is the area of that trapezoid. And so my total area there is 3,200, or this comes out to be part A, if my iPad will write, is 3,200 people. And again, it says show the work that leads to your answer, so I would want to show that work that I did up there. Now, is the number of people waiting in line increasing or decreasing between t equals 2 and t equals 3? So let's think about the people that are waiting in line. There are 700 people to start, right? There are 700 people to start. People arrive at the ride, and then people get onto the ride, right? So the length of the line is the rate that people, or is the integral of the rate people get on the line minus the rate people get off the line, right? That would be my line length. So let me write that down just so we know it. People waiting in line. This is the people who have arrived minus the people who've gotten on. Okay? The rate of people that arrived minus the rate of people who've gotten on. So is that number increasing or decreasing at between t equals 2 and 3? So let's think about it. We know that the rate people are getting on the ride. People are getting on the ride at 800 people per hour. They told us that. So let's look at the rate people are arriving. So if I look at this graph, the rate people are arriving, and I'm looking between t equals 2 and t equals 3. So here, this region right here, t equals 2 and t equals 3. Now, notice what happens. At t equals 3, it is exactly 800 people per hour, right, arriving. But before that, between 2 and 3, notice we've got more than 800 people per hour. So what I'm looking at here when I really think about this is that arrived, I know that this is more than 800 per hour. Gotten on, I know, is less than 800 people per hour. So the number of people waiting in line should be increasing. Right? Because the rate people are arriving, which I know is R of t, is greater than the rate people are getting on the ride, is greater than the rate people get on the ride, which is 800 people per hour. Okay, 800 people per hour. Okay, what other questions on that? All right, we're going to skip C&D for right now. We're going to do one last one. I had planned to do an hour, but we have no questions. And so we're going to do 45 minutes and see how this goes. Okay, so this one says, the rate at which people enter an auditorium for a rock concert is modeled by a function R, given by this. So this is the rate people enter between 0 and 2 hours. R is people per hour, so this is a rate. No one's in the auditorium when it opens. So this tells me my initial equals 0. The doors close and the concert begins at t equals 2. So how many people are in the auditorium where it begins? Well, I'm given the rate people arrive or enter. So to find the number of people, for A, I'm going to look at the integral from 0 to 2 of r of t dt. Right? The number of people that arrive. And so that should be, actually calculating that out, 980 people. Okay, part B says, find a time when the rate people enter the auditorium is at a maximum. Justify your answer. And part B, I would encourage you guys to look on your calculator. So I want to know when it's a maximum. So I'm going to look for when R changes from positive to negative, right? That's where maximums happen, positive to negative. So when will it be at a maximum? Okay, so think about it. I'm actually going to think about what this graph would look like. This graph is going to look kind of like this. And again, I would graph this on my graphing calculator, but I don't have one I can play for you on my iPad. So this is a cubic function. It's a negative cubic function. And I will tell you the zeros of this function are 0 and are 1.36269. Okay? And it's going to look like this. Actually, hang on a sec. It's going to look like that. So which one of those is my maximum value? So looking at your graph, I can see that this is tangent there. I can see that there R actually goes from a positive to a negative. And so what I'm going to look at here is that the maximum is at t equals 1.362 or 363, depending on whether you round or truncate, because your R, your rate, right, your R of t changes from a positive to a negative.